train the Autorouter with some rules to achieve better results. So we want to eliminate some of that wrong way routing by using some layer bias techniques, and also we can prevent side entry out of surface mount pads, out of rectangular pads, things like that. So we'll show you a little bit of that. So the first slide here is preparing your board for the Autorouter. So we can define regions on the design to constrain the Autorouter. And the region types include route keep-ins, which is going to establish the barrier where the router cannot exit out of. So this is going to be some barrier to the inside of the card outline. The route keep-out can be established by layer if need be, or I can have route keep-outs that apply to all layers. And I can also have via keep-outs. If I have a particular device that maybe has a copper heatsink or a tab of that device that's going, to lay down on that piece of copper feature, obviously I would want to keep vias out of there because I wouldn't want to short those signals, to the tab of that device or things of that nature. And this is just kind of showing you an example. These are 3 different route keep-outs. The first one is a route keep-out around like a mounting hole or something like that. And you can establish different stipple patterns now. In version 16.6, we allow you to assign a particular graphical stipple pattern to that. And so you can associate not only a color, but a particular stipple pattern. So visually, you can identify them in the database. You don't have to go into the layer color dialog and try to figure out which shapes are tied to what. So the stipple patterns help you identify those. So this one's a route keep-out on all layers. This is a route keep-out on the bottom layer with this particular stipple pattern. And this is a via keep-out with this Argyle pattern attached to it. And you'll see those in the database. The next thing is we can define the route keep-in using the zcopy command. So zcopy is a very powerful command. It has a number of uses, but in this particular application, I simply want to copy the card outline, and I want to shrink it or contract it by 25 mils in this case. So what I'm doing is I'm creating a route barrier here, so any of the auto routing cannot go beyond this barrier. It has to stay within this route keep-in. This also applies to when I create copper pores. If I'm creating my plane layers, whenever I pour the copper, it's only going to pour up to the edge of this barrier. It will not go beyond that. So most times you would always want to pull your plane layers back away from the card edge or a card outline so that when the board is manufactured, I don't have copper all the way out to the end where, if it's placed into a chassis or something of that nature, that I can't short those planes together by some metal contact, to the edge of the card. So that's why we always pull the power planes back away from the card outline. The next thing is fan-out creation. So fan-outs for surface mount devices, this establishes routing points on all the internal layers so that we can get to it with the Autorouter. And we have a very powerful command within the PCB editor to create these fan-outs. And we have quite a bit of control. We can choose the vias that we want to use for the particular fan-out. We can also choose the fan-out style for the particular desired direction, depending if it's a VGA or if it's a connector or things of that sort. And the pin via spacing options can be used. In that first slide, I showed you that connector where all of the vias were in a line cutting off the routing channels. Well, the pin via spacing parameter down here, we can also enable this minimum channel space, which helps us open up those type of issues, and I'll show you that in the demo. So there may be parts in the design that may, where the typical fan-out may not work for you on the, because of the pin pitch of the device. So in this case, I have a 0.65 millimeter BGA, and this is an example of a part where the typical fan-out is not going to work because I simply don't have enough room in between the balls of the BGA, which you see here in green. The vias are actually what you see in orange. So what I did in this case is I created in the LAN pattern or in the footprint of the device, I created some pin escape scheme or fan out scheme to enable the router to get to these via points here. And once I figured out what this scheme is going to be, I was, save that as part of the LAN pattern or part of the footprint. Because once I figure out what this is going to be, why would I want to recreate the wheel every time I, come up with this particular device that I have to use? And also, I might have multiple parts that on the board that employ this same footprint. So by placing it as part of the LAN pattern, that solves that problem for me. And here, I'm just showing you a screenshot in the actual footprint editor. You can also employ the Create Fanout tool there as well. And then, of course, as I mentioned, once a solution's developed, you can save that as part of the part. The next thing we're going to talk about is layer polarity. So in the stack up, if you go into the cross section of the board, you can see all my various plane layers. So I have my ground layer, I have my 3.3 volt plane, I have a ground earth, and I have another power plane. So these particular layers or plane layers are designated as negatives. And this is so that I can take it into the Autorouter so that the router will handle it correctly. One other thing to mention too is when we do the fan out for all of our devices, the reason we want to do that up front is because we want to make sure that all of the devices on the board have connections to the power and ground layers. And the reason we want to define the power and ground layers is because we don't want the router to try to route those as signals. So if we tell the router up front that these connections are already made and they're connected to planes, then the only thing the Autorouter is going to look at are the signals that we want to route. Here's just showing you some critical pre-routes. So here I have some differential pairs that have connected to this BGA, as well as a clock line that has some length assigned to that particular net. And anything that I do in the PCB editor, when I take it into the Autorouter, this will be received in a protected mode, and the router, obviously, protects the status of those. So they cannot be changed by the Autorouter in any way. I have to physically go into the Autorouter and disable the protection if I wanted to do that. And so the default setting is that they do come in protected. And then launching the Autorouter can be launched directly within the PCB editor. You could also run it standalone if you want. There's a number of different modes that you can run it in here. So you can run it in what they call a route automatic, which will give you a simple little GUI, and you can go in and select number of routing passes and things like that. There's also a route custom, which kind of lets the router try to figure out the board and come up with the result for you. And in this case, I'm running the route editor. So when I run the route editor, anything that I have in the PCB database, as far as my physical and my spacing constraints and any rules that I have, my via selections, all of that is passed directly to the Autorouter. So I don't have to come up with any elaborate rules or anything for the Autorouter. Everything that's in the constraint manager already is automatically going to pass to the Autorouter, and that's a nice integration feature that we have. So let's talk about a route strategy file. So this is what we call a route do file. So we're going to do what's specified in this particular instruction file. So it's referred to as a do file. And we can provide very specific routing instructions. We can select components to be routed first, or nets, or net classes. So I can selectively pick and choose what I want to have happen first in the actual Autorouter. Route order and priorities can be set. So if I'm routing multiple net classes and things like that, I can also assign higher priorities to one over another. I can also assign costing parameters to define, layer directions and things like that, which I'm going to talk about in a minute. Also, if I want to cost, or prevent, side exit out of rectangular paths, if I want to cost control, routing on certain layers, if I want to make it more difficult to route on one layer versus another, these are example of, costing parameters. And of course, layer selection, we can unselect or select particular layers that we want to route on, and we can also control, the routing directions on those. And of course, the number of routing passes and, things that we have in our strategy to, enable that we get a success on the design. So here's an example of the route do file that we're going to launch to actually route this particular design. So the pound characters that you see here are simply comments. So what I've done here is I've put in the actual comment of what we're going to control with this particular command. And in this case, I'm doing a cost side exit forbidden. So this prevents any kind of routing coming out of the side of a rectangular pad on a surface mount device. And it also prevents it from coming off in an odd angle or off center. So it has to come out of the center of the pad. The next statement is a layer bias. So this tax way statement keeps everything very horizontal and very vertical as far as the routing goes. And in the next statement, I'm just simply unselecting all the wires in the design. I mean, I shouldn't have any that are selected to begin with, but this just ensures that everything is unselected in the design. And then I'm simply turning off the component boundaries because I really don't want to see those. I just want to see the pins of the devices. And now we actually get into the setup for the Autorouter. So down here we have a wire and via grid that we set up to actually do the auto routing. So in my case, I'm choosing a 5 mil via grid and a 1 mil wire grid. And to make this design a little bit more challenging for the demo, I'm also unselecting the top and bottom layers. So I'm only allowing the actual design to have 2 layers to route on. And then up here is actually where we get down to the business of doing the routing. So I'm going to start off with 25 route passes, and there's some key algorithms in the Autorouter itself. And once it finishes the first 25, if it does not complete it in that time, it'll go to this next route command, which routes another 50 passes, starting from pass 16. So this is a key algorithm in the Autorouter. After we execute these, it runs 2 clean passes, or optimization passes, if you will, which will clean up or optimize any vias. So if it can be routed in a shorter manner and with less vias, it will pull out the vias and so forth. And then after we optimize it, if it still needs to, if there's still disconnects or still conflicts, the router will go into a second phase here, and it'll do another 50 passes starting from pass 16. Now, all of these are kind of in here as a safeguard. If the route completes in the first 25 passes, then it really skips over these next routing phases. So it doesn't have to route every single one of those route passes, only if it's needed. And then at the end, we'd run 2 clean passes. We run a command called critic, which eliminates staircasing, and it does some more optimization. And then we want to set up the board so that it's more appealing for manufacturing. So we can disperse, if I have a group of traces that are kind of crunched together, but I have all kinds of space around it, we can use this spread function, and the spread function will kind of disperse those wires across that empty space so that they're not all bunched up together. And it just, makes sense for, better manufacturing. If I can provide a larger, clearance between objects, then that's very desirable. The last one here is a center. This centers the actual wires between through-hole pins. So instead of, hugging one edge of a pin it'll actually bump the wire, down through the center of the pins, to provide extra clearance. And then the very last thing that we do is we miter all of the traces. So this route engine routes everything orthogonally. So it'll have a 90-degree, turn in all of the routing that you see initially. And then at the very end, we do this miter function, and it miters all of the traces to a 45-degree in this case. And I have some bend options in here, so I'm telling it I want it to make a 50 mil bend starting at 5 mils, coming out of the pin or coming out of the, off the bend. The pin, I have a 25 mil, exit before it creates a 25 mil, 45 degree. And also I'm have a slant, any 45-degree slants they have in the actual traces, I'm telling it that's what I want, for my beveling. So it's a fairly, easy do file here. This do file can be used on probably 90% plus designs that you have. This will work, for most any design that you'd want to throw at it. You could modify this slightly, if you have a net class that you want to route first or a particular component, you could just slightly modify this, and this would be a very good route strategy for most boards. When we're done routing, let's take a look at the results. So here you can see I have my 2 routing layers. So you can see the layer bias. This is a vertical layer. Now, because I've restrained, this Autorouter to 2 routing layers, you are going to see some wrong way routing in here, just simply because I only gave it 2 routing layers. But predominantly, you're going to see this blue layer is the vertical layer, and the brown layer is the horizontal layer. So you do see a little bit of wrong way routing in here, but it's because I've really constrained the router to 2 layers here. You'll see that if you add additional routing layers, you'll see that there's more horizontal and more vertical layer biasing, even more than what you see here. So I just wanted to preface it with that. So this is predominantly because I only gave it 2 routing layers. This is the route status report that you would see. So this tells me my completion rate, how many connections I have, and things like that, how many total nets in the design, and statistics about the board itself. So once I'm completed with the route, I would simply create a session file. So I would write that session file, and that's what we take back to the PCB editor. So once we have it back in the PCB editor, we can also employ some other what we call route glossing features to further optimize the results of the Autorouter, because there's some additional things that I can control in the PCB editor. So if there are any leftover 90 degrees because my miter command, maybe my offsets that I had in there, left me with some 90 degrees, coming out of very short distances out of pins, this optimization here will take care of that. This can also be used, maybe not so much for the auto route, but if you did an ECO to a board and you rerouted some traces, but you had a little tiny piece of etch that just kind of standalone in the board, by running this glossing technique here, this will actually remove what they call that dangling line. So even if it's a little speck that you missed, in the process of doing your ECO, this is another use that you can employ this glossing on, and it does a very good job. And then the last thing is we can also add fillets or teardropping to a design. Now the reason we'd want to do this is especially when we get into fine line design. So this is that 0.65 millimeter component. These are 4 mil traces and spaces in here. Well, what happens is when you get into these type of fine line designs, whenever you have a very fine line coming into the pad, the entry of a pad, we have a very sharp entry point which comes into that very small pad. And this creates, or can potentially create, a reliability issue, because if the board is subject to any kind of vibration, or depending on the environment that it's in, you can actually have what they call a fracture point occur where this trace enters the pad. So by adding teardrops, the teardropping actually puts a dynamic copper shape over that entry point where the trace comes into the pad, and it adds more copper. And because I'm adding more copper, or this teardropping feature, I can really improve the reliability, or preventing the fracturing of that trace coming into that pad. And this is a screenshot of the actual parameters that you can control. So you can control all of the different types of pads that you would have, as well as different fillet options and so forth. And so this is ultimately what we'd like to achieve. So this is actually a pretty good result. So let's go off and demo it and actually show it to you. So here's my design. First thing I'm going to do is point out that I have some route keepouts here. So the route keepouts that you see in red, these are around mounting holes. I also have some via keepouts, so you see in that blue stipple pattern, these are via keepout regions that I have underneath the connectors. I also have a route keepout on the bottom layer underneath the tab of this device, because this device is a voltage regulator, and it's on the, actually in this case it's a connector. I thought it was a voltage regulator, but on the back side, because it's mounted from the back side of the board, I want to prevent any vias from being underneath this particular connector. The next thing I'd want to do, oh, and one other thing, in the constraint manager, we also have the ability to set a clearance from just a plain drilled hole in the design. It can be an unplated drilled hole, like you see these mounting holes. So I can set up a clearance from any trace or any via or pin, or any shape that's going to be poured around these unplated holes. I can set a DRC distance. I don't have to necessarily use a route keep out. I can simply put in a clearance, and I can set clearance to those particular objects. So I'm also showing you here that you don't necessarily have to have a route keep out. Whatever I have set for my hole to line clearance or hole to pad clearance, that's directly passed to the Autorouter from the constraint manager. So there's a number of ways you can utilize these route keep outs or specify clearances. The next thing I want to do before I do my fanouts is I want to establish my route keep-in region. And the way I do that is I'm going to go up here and I'm going to say edit Z copy, and I'm going to set this to my route keep-in layer, all layers of the design, and I'm going to use a 25 mil clearance. So it doesn't matter what shape or what contour of the board is, it's going to copy that shape exactly when I use that command. So here I just made a copy of the card outline, and I shrank it by 25 mils, and it's now on my route keep-in layer. So now any copper that I pour is only going to pour up to that edge of that keep-in, and also it's going to prevent the Autorouter from doing any routing out here near the edge of the card outline. It can only go up to this particular barrier. So the next thing I want to do, and let's just tell you a little bit about the design itself. So in this particular case, it's an 8-layer design. I'm going to be using an 18 mil via with an 8 mil drill. The default trace and spacing rules are 5 mil trace and space. And there's an area of the board that utilizes that 4 mil trace and space, and that's that particular Fineline BGA, the 0.65 millimeter. There's 3 BGAs total. There's 2 on the top side and 1 on the bottom side. And the pin pitches are a variety. I have a 1 millimeter pin pitch a 0.8 and a 0.65 millimeter. So I'm just kind of showing you that you can have some fairly complex LAN patterns on the board, and we can effectively handle that in the Autorouter. So let's go ahead and create some fanouts now. If I select my fanout icon here, over here in my options console, I have the ability to, if I had more than one via to choose from, I could select whichever via I wanted to use. In this case, I want to override, and I want to use a specific trace width. In this case, I'm using 10 mils, and I'm going to use this for my connector because I want a beefy, connection coming out of the connector. And then I can also have this minimum channel space I have set to 15 mils because I want to prevent, when I do fan outs on the connectors, I want to prevent any of them from being, cutting off my routing channels. And if I zoom into this area, you can see I can do individual pins. Like say I just, select these pins individually. I can do it that way. I could also swipe a window around pins, and I can have it fan out that way. Or I can go to my fine filter, and I can select symbols. And now if I just simply tag that footprint, I can do the entire footprint in one button click. So now let's go ahead and do the fan outs on my VGA. So I'm going to uncheck that. Let's change my direction to my VGA quadrant style. And my pin via spacing, I want to center the vias in between the balls of the VGA. So if I tag that footprint now, you notice also it only fanned out the active pins of the device. So some of these pins down here did not get a fan out. If you wanted to include those, you could include these unassigned pins, and I can just simply go back and tag it again, and it adds those remaining ones in there. So I'm just going to use, let's just cancel out of this for a second, and I want to use just the active one. So, and it looks like I canceled out my other one. So let's just go back. Oops. Let's just go back and redo this. Sorry about that. So again, I'm just going to repeat what I did. I'm going to swipe a window around these so you can do it that way. My fine filter, I'm going to go up here and select this as a symbol, and I'm doing those outward. I'm going to take off my override line width. I'm going to do my VGA quadrant style now, and I'm going to center those in between the pins. So I'm just doing my active pins. I'm going to select my VGA that's on the bottom of the board, so you can see it did the quadrant fan out the same way as well. Now what I want to do is I have one device that's not placed on the board right now. So I'm going to pick that device, and I'm going to place it on here. I'm going to show you if I do the VGA quadrant style and I select that part, obviously you can see this is not going to work for this device. So my vias are in purple, and you can see there's just simply not enough physical room inside the VGA to employ that 18 mil via. So what do I do in that case? So in this case, I could build my own pinout or pin escape scheme that I know will work for this design. So let's delete this part back off of here. And what I did back in the schematic in Capture is I specified an alternate footprint that I could use. So here I'm going to choose the alternate, and now you can see I've employed that pin escape scheme on the alternate footprint that I used. So let's turn on my trace layers. I've pre-routed some clocks and some differential pairs in here, and I'm just going to go ahead and place that part now. So by utilizing this pin escape pattern that was used in my alternate footprint for this symbol, you can see that I have very easily pin escaped this part, even though it's a very fine pitch device. And the key is, because of the channel space in between each of these vias, I now allow the Autorouter to effectively get to those routing points very easily, and I don't cut off any route channels in the process. So that's the whole point of, these complex, parts. We can actually build a pin escape scheme that's going to work for the Autorouter. So now I've done all of my pin escapes. The next thing I want to do is I want to ensure that I have power distribution for the entire design. Now, I've already done most of the power and ground layers, except for one, just to kind of demonstrate how you can do this. So I'm going to do an edit, split plane, create, and I'm going to pick the layer that remains. In this case, it's my 3.3 volt layer, and I'm going to create dynamic copper pores now. So the first one is, and I have a split plane here, so I'm just going to use my net filter to filter out the ones that I don't want to sort through. And then I know that the rest of this plane layer goes to 3.3 volts. So now I have all of my power distribution is done on the board. All of my planes and split planes are established. All of my power and ground fan-outs are done, so I have connections to those devices. So now the Autorouter isn't going to try to route those as a signal, because I've already established the connectivity. So let's turn off my 3.3 volt plane layer now. And one last thing, let's go into the cross section. And in the cross section, you can see my 3.3 volt and all my other plane layers are set to a negative polarity. So this ensures when I go into the Autorouter is going to read it properly. So now let's take it into the Autorouter. So I'm going to execute the Autorouter. So I've just launched the Autorouter. It passed all of the design information from the PCB editor directly into the Autorouter. I like to reset the colors in here because I think it shows up a little better. So I'm just going to restore those to the router default. And let's repaint it to clear up the screen here. So I'll close that. And now what I want to do is I want to execute my do file. So the do file that we reviewed earlier in the presentation, I'm going to execute that now. So I'm going to go out and grab that. This is just simply an ASCII text file that I created with those instructions that you saw in this slide. And I want to launch this now. And the first thing that pops up here is I'm running OrCAD PCB Pro is licensed I'm running. And when I launch the Autorouter, it recognizes that I have a differential pair routed in the design. Well, this particular version of the router doesn't support auto-routing differential pairs, so it's saying I need a route fast option if I was going to auto-route those. But since I pre-routed them, I'm just going to ignore this. And I'm going to launch the Autorouter now. So the first 5 routing passes, what you're going to see is all it's going to try to do is accomplish full connectivity, and it doesn't care how that's done. There'll be crossovers where the traces route on the same layer over top of one another, and clearance violations. We've already gone past 5. So you see on my status line, there are 0 unconnects. So everything is connected at this point. However, I have 14 conflicts that it's trying to resolve, and it's going through the various algorithms to resolve those. And it's using rip up, retry, and shove to achieve those. So as it goes through each of the routing passes, you'll see these conflicts change, and you'll see the completion rate change until the design does what they call a full convergence, where all of the route conflicts have been resolved and there are no unconnects on the design itself. So this will take just a few moments. Again, I've constrained the Autorouter to 2 routing layers only, just to simply show you, a board of this density with, these different pin pitch devices. I can still effectively route this with the Autorouter. So we're coming up on past 50 here. I've got 1 conflict left. It's going to do a clean right now. It did disconnect 1 wire. And now I'm hitting it with another route phase to remove those last conflicts. So now I'm at 100%. There's no conflicts left. I'm doing another optimization pass, and now I just did my miter as my last function. So right now, the board is 100% routed. There are 0 conflicts and 0 unconnects. You can also display the route report here, and it'll show me all of the route statistics for the design. Of course, I can save this to a hard copy report if I want to, and so on. So now let's actually take a look at it. So if I turn off all my layers, and I look at the top layer, because I told it I didn't want any routing on the top and bottom layers. The only routing that you see here is because I have a split plane, and this particular connector over here, didn't connect to that split plane, so it added a little bit of copper here to get to that split plane. Outside of that, there's no routing on the top or bottom of the layers. So if I employ the bottom layer, you can see it's very clean. There's nothing there. If I look at the internal layers now, you can see I told it this was going to be my horizontal layer. So you can see predominantly all of the routing is horizontal, with the exception of up in this area. And again, it's because I've severely constrained the Autorouter. The only way it could get these last couple of connections was to employ a little bit of wrong way routing here. If you look at my other layer, it's very vertical. So that's what that tax statement does for me. Now, if I zoom in here and actually look at the quality of the routing, it actually is pretty good. This trace right here, maybe I could improve this a little bit. If I turn on the other layer, you can kind of see, the Autorouter is not entirely perfect, so maybe I could improve that. And this is an option that you could do. So maybe I take this, via here and I slide it. Maybe I want to shorten this a little bit and get rid of this loop here. So just kind of showing you that, and I'll unselect that. So just showing you can optimize some of this stuff. You could do it either here or back in the PCB editor. But I mean, for the most part, it's a pretty clean design. Here I have, one of those 90-degree corners. Again, this could be the result of my beveling parameter, or maybe I want to make this a little bit longer corner. So you can go in and clean up some of this stuff. I'm going to leave that one because I'm going to take it out with the glossing. So for the most part, I have a pretty clean route. So let's go ahead and save this now. So I'm going to write what they call a session file. And now I'm going to exit the Autorouter. And it also records whatever you did to a text file called a did file. I don't really care about that, so I'm just going to delete the did file. And if I come back now to the board, let's go back to my board. Here it's merged those results. So if I look at the actual route, so I might see some things here like I have this double via here. Maybe I could do that a little bit better. So there might be a little bit of cleanup that you want to do, but for the most part, the Autorouter's saved me a great deal of time. I routed this board in less than 10 minutes. So maybe I'd do a little bit of cleanup. If I was going to route this by hand, I would probably spend maybe an entire day doing this, or maybe even longer than a day, trying to figure out a solution for this. So let's go ahead and employ some of my glossing techniques now. So if I go to the gloss menu, I'm going to go to my line parameters, and here I can pick and choose those things that I want to try to eliminate. So I'm just going to go ahead and gloss it. It'll do a little bit more optimization. If I go up and I look at that layer that we looked at in the router, and I think it was up in this area right here. Yeah, so I think it was this trace right here. It had the 90-degree corner on it. So you can see by further glossing, I've really kind of optimized and cleaned it up even more. So it looks a little bit more desirable. If I look at the other layer, you can see, again, it looks very clean. So I can achieve a pretty good result. So now, last but not least, let's talk about teardropping. So what I want to do is, if I look at my top layer, If I look in the area of this BGA, I have all of these very, fine line traces coming into these balls of the BGA. And again, this is where we could have those potential fracture points. So by adding teardrops, we can, improve the manufacturability of this board. So let's turn on all my layers again, and let's go up here to my gloss, and this time I'm going to add a fillet. If I look at the fillet parameters, this is kind of a review. Of course, you can choose what you want to add a fillet to. Is it a pin or vias only, or T's, or in this case, I'm going to say add fillets to everything. And you can also choose the maximum size pad that you want to add a fillet and so forth. So I'm going to go ahead and accept that. I'm going to swipe a window around the board, and I'm going to say add fillet. So if I go into my gloss, add fillet, and I'm going to swipe a window around the board now. So now it's adding all of those fillets. A common question that might come to mind is, okay, I've added all the teardropping to this. What if I have to modify or edit this board now or do an ECO to it? So you can just simply reroute any traces that are affected by the ECO, and you can re-teardrop it. Or you can even remove teardrops, globally on the board. So I have a couple of devices. These big decoupling caps, I pre-routed these with these, because they carry more current. So I've pre-routed these by hand because I wanted multiple vias. However, I don't necessarily want this teardropping on here. So I'm just showing you that you can kind of selectively remove those as well. So if I select that part and maybe this part, I can selectively remove the teardropping from those. And now I have only teardropped what I'm interested in on the board. And if we take a look at that, let's go back to the top layer. If I view in that area, you can see the shape that's been added now to the edge of this trace coming into the pad. So I have a little bit more copper feature spread out coming into the entry of the pad here, which gives me a much more reliable connection. So in the end, this is my end result. So it's a pretty clean design. Again, you might have to do a little bit of cleanup, like maybe I don't like this very long diagonal here. I can go in here and just simply slide it and do whatever cleanup that I want. But I have a pretty effective result in a short amount of time. And if this was a board with 10,000 connections on it, I could probably save myself probably a week in routing or more. So with that, I wanted to open up 2 more poll questions. So this is our end result, as we just showed. So I'd like to open up the polls for the last 2 poll questions. So based on today's presentation, do you think you would benefit from using an Autorouter on future designs? So I hope today's presentation really gave you some good insight into what you could do with the Autorouter. And again, I didn't employ a very complicated route strategy. You can take that route do file that we just showed, and you could apply it to any board, and then you could just add, whatever particular, things that would be different about your board. You could, for example, route another net class, first, or things of that sort. And then the last poll question is, what additional webinars would you like to see from EMA? Maybe constraint-driven design, PCB layout file management, advanced interactive routing techniques, library creation and management, or any kind of ECAD, MCAD collaboration. So these are some suggested formats that we could probably do. So if you would go ahead and pick which ones would be pertinent to what you would like to see. Okay, and I think the polls, are they just about closed? The polls are closed now?
Polls closed. Mm-hmm.
Okay, and I'd like to thank everybody for joining us today. And if we can help you out, or if you have any additional questions, please contact us, and here's our contact information. And I'd like to thank everybody for their time today.
Thanks, Rocco.
Thank you all. Bye now.
The organizer has ended the session, and this call will be disconnected. Goodbye.